Well, welcome everyone to our final lecture. If the entire course so far has been a story of how humanity prepared to search for life, then today's lecture is about what happens next. Because the future of astrobiology is not distant science fiction anymore, but it's being literally built right now in clean rooms, in Arctic field stations, in supercomputer clusters, and laboratories where protocells divide in petri dishes. The next 30 years, roughly 2030 to 60, are likely to be the most transformative decades in the history of life detection, and you, sitting in this course, you actually live in the generation that will witness it. So, before starting the future prospect and what this lecture covers, um, I need to cover a couple of things that we actually missed before. One would be the Fermi paradox. So, where is everybody? So, Enrico Fermi is having a lunch with physicists at Los Alamos in 1950s, and they are talking about UFO sightings and space travel. Then Fermi suddenly stops eating and puts his fork down and says, "What? Where is everybody?" And the table goes silent. That's the origin of the Fermi paradox, one of the greatest unsolved problems in astrobiology. How to explain it, how can be explained? Well, think about it. If the universe is full of planets, full of organic molecules, full of water, why don't we see anyone out there? So it only takes 10 million years for a civilization to travel across the galaxy at slow speeds, extremely short in cosmic time. The galaxy is 13.6 billion years old, older than all evolutionary timelines on Earth. And we should be seeing megastructures, beacons, probes, but we see silence. So there are different uh, stories, possibilities on how to solve this. One would be the rare Earth hypothesis. Maybe we are special and there's a great filter. Maybe something kills civilizations. And there's a zoo hypothesis. Maybe we are being observed and dark forest. Maybe everyone is hiding. And these are really interesting science fiction and ideas that you can also find many discussions online. The universe might be full of life, just life that's smart enough to not answer unknown phone calls. And another thing I would like to talk about would be the Drake equation. So it's 1961 in Greenbank, West Virginia. A group of scientists gathers again for what is basically the first real meeting about the search for extraterrestrial intelligence. And the middle of the chalkboard, Frank Drake writes something that forever changes our field. It's the Drake equation here. He didn't intend this to be the precise formula. He wants that it was meant as an agenda for the meeting and not a scientific equation, but it stuck. It became the DNA of SETI Institute thinking. And so the Drake didn't try to mathematically predict aliens, he simply broke a huge, terrifying question: are we alone into small, manageable scientific pieces? So, star formation rate, how busy is the galaxy, and fraction with planets tell them how nobody knew this number until Kepler, and planets with liquid water, and then um, fraction where life actually begins, and then life that becomes intelligent, and life develops technology, and the big outbreak, how long civilizations survive before they destroy themselves. So this last variable, L, terrifies and fascinates us. It's the only one we can actively change, to be fair. And also, I would like to talk about the Dyson spheres. So this is Freeman Dyson. Actually, in his paper, Search for Artificial Stellar Sources of Infrared Radiations, he actually joked and said if an advanced civilization really wants maximum energy, they might as well build a shell around their stars. Haha, just saying. And it really stuck, and Dyson Sphere became a thing, and people misunderstood. Well, actually, it also made a bit of a sense, but not so much. And then Dyson said people misunderstanding him. He wasn't suggesting anyone build such a thing. He was only saying if aliens built it, we could detect it. So the concept wasn't meant as a blueprint, but as a detectability argument. Um, for 2 months in 2015, well, okay, let's move on. Um, so then the Soviet scientist Kardashev, has been created a scale where displaying the type of civilization are developed they were type 1, and these are not just planetary level but also the scientific level on earth and their health, etc. So type 1 would be capable of controlling the energy of the planet they inhabit, and type 2, based on Dyson sphere, controls the sun of the energy of their solar system, basically. And type 3 would control the energy of the whole galaxy, etc. These are really uh, sci-fi ideas, actually. But yeah, even though he was joking, the idea stuck and made a bit of a sense. But now we can actually continue with our lecture on upcoming missions. So think of this section as a preview of humanity's greatest future explanations. We will return Jezero crater samples. We are going to Europa. We are going to Titan and Enceladus and sample returns, and there's ELT, and we all gonna explore each of these. Um, so Mars sample return. Uh, there's a personal anecdote when many NASA engineers share when they talk about Mars sample return. They say this is Apollo 11 of our generation, and why they are saying that because retrieving samples from another planet is unbelievably hard. So Perseverance collects them. A lander will arrive with a rocket. The samples will be launched into Martian orbit. An orbiter will catch the container and return to Earth. This is most complicated space mission ever attempted, and inside those tiny tubes, ancient mud from a 3.5 billion years old lake delta. If life ever existed on Mars, this is where its fossil would be hiding. The day these samples land on Earth will be one of the biggest scientific events of the century. So look out for that. And also the Europa Clipper. Europa is a strange world. The ice shell is 20 kilometers thick, and below it is an ocean containing more water than all Earth's oceans combined. The seafloor may have hydrothermal vents, and this is the closest analog to early Earth we know. Clipper will analyze organics, salts, thermal activity, chemistry of potential plumes. So the idea that Europa had an ocean was originally dismissed as fringe. It was Carl Sagan and a handful of dreamers who insisted we take it seriously. Now it's one of NASA's flagship missions. And for the Titan Dragonfly project, this mission is so bold that when it was first proposed, the joke inside NASA was wait, we are actually approving this. Dragonfly is a nuclear powered flying drone that will hop across Titan's dunes and riverbeds. Titan is the only other world with rivers, lakes, rain, and stable liquid on the surface, but everything is made of hydrocarbons. Some prebiotic chemists say Titan resembles Earth before life, and Dragonfly will test complex organics, prebiotic reactions, and potential chemical pathways toward life. If methane based life exists anywhere, Titan is a prime candidate, and Enceladus sample return. It's a proposed mission. It's a Enceladus is a cosmic miracle, as we discussed in the previous lecture. It is literally spraying material from its surface ocean into space like a natural delivery system from an alien ocean. A future mission may fly through the plumes and collect organic molecules and detect amino acid, lipid, or even cells. Imagine the headline: "Life confirmed on Saturn's moon." This is not science fiction. We already know the ocean contains organic salt and hydrothermal activity. The rest is waiting. And there will be great telescopes like ELT and LUAR. These telescopes will make James Webb look small. Extremely Large Telescope ELT, a 39 meter monster in Chile, it was directly image Earth-like planets. And there's Hab X, designed specifically to look for oxygen, ozone, methane, and water vapor, basically atmosphere sniffing. And LUAR, the Dream Telescope, a multi-wavelength behemoth that could image continents and oceans on distant exoplanets. You will hear this phrase a lot in NASA presentations. LUAR could take the first portrait of a living world. Think about that. A photograph on another Earth. So let's continue about the possible breakthroughs that might happen. Biosignatures. We might find life and determine what biosignatures should be. So methane, oxygen, boom life, DMS on terrestrial exoplanet, boom biology. This discovery will not be a single headline, it will be long debate. And there would be direct imaging of exoplanet surfaces, oceans reflecting starlight, cloud patterns, glint from liquid water, seasonal changes. One of the LUAR team lead once said the first time we detect continents on another world, philosophy departments will collapse from shock. There would be lab created evolving protocells and synthetic life. So now we can make protocells that grow, divide, and encapsulate genetic material. Within 20, 30 years, we may see protocells that evolve, metabolic network emerging spontaneously, ribosome-driven protocell species competing. If we create evolving chemistry in the lab, that is not life as we know it, but as it could be. It will redefine biology. And there's a possibility of ocean worlds and inhabiting having a life. A confirmed biosignature in Europe or Enceladus would be the biggest discovery in human history. It would prove life is not rare, not fragile, life emerges wherever conditions allow. And there could be a second Genesis event. This is the Holy Grail, a form of life that uses different handedness, uses different nucleic acids, uses different biochemistry not related to Earth at all. If you find an independent origin, even microbial, one thing became obvious: life is a cosmic phenomenon, not an Earth phenomenon, and humanity will never look at itself the same way again. But there will also be challenges ahead. The planetary protection. So, what it is? Dose of reality. As we push forward, we face moral questions. What if we contaminate another world? If we seed Mars with Earth microbes, we will never know if Martian life existed. Planetary protection is not just a bureaucracy, it is an existential responsibility, including the sterilization of spacecraft, preventing Earth microbes from colonizing Mars or Europa, preventing alien samples from contaminating Earth as well. A single mistake could destroy the greatest scientific question ever asked. Interestingly, Carl Sagan was one of the earliest voices arguing for strict planetary protection. Even back in the Viking era, he said if we contaminate Mars with Earth life, we steal from ourselves the opportunity to know for certain what was there. So the planetary protection originates from um, back in um, 1967 with a space treaty, and it was signed and included a section about these contamination risks and bringing life back to Earth or bringing life to those planets. So there are lots and lots of ways and lots of the categorization and risk involved in this idea. But the thing is, there's a dormant bacteria, non-spore forming dormant bacteria as well. In the new findings, I might try to add those paper as well, and it became something that we may not be able to control. And we are sending astronauts, that means that we are sending trillions of cells and bacteria into there. So it is challenging, and it's an illusion to think actually you can control it. And the question should be what happens after the contamination. This would make more sense to me, because even after the contamination you can eliminate the contaminants. 98% or 2 can develop a resistance, and if there's an environment they can thrive, then the result would be the same, because they would multiply very fast. So this is, and they can interact with the current life there with their bacteria and actually make things very hard. So this is a very big challenge and very big debate about how those space missions can be made, considering the planetary protection system from extremophiles and different bacteria. So this is the end of our lectures. So let's summary the entire course. So we began with ancient myths, and humans have wondered about life's origin 50,000 years back, and then philosophers like Anaximander, Democritus, Epicurus, these cosmic thinkers introduced uh, thinking. Then 19th century Pasteur and Darwin killed spontaneous generation and universal common descent, and 20th centuries with Oparin and Miller, Viking missions and Antarctic meteorites, and the modern interdisciplinary science, NASA Astrobiology Institute, Cold War, Mars rovers, ocean moons, exoplanets, James Webb Telescope, synthetic biology, and now we are on the edge of empirical detection of life. Humanity has climbed 50,000 year ladder, and we are now reaching for the final rung. So, as for the key takeaways, I put Giordano Bruno, the father of astrobiology, in this section. Astrobiology is an ancient but newly integrated field. It unifies chemistry, biology, geology, astronomy, so it's interdisciplinary field. Every major discovery accelerates the field, and we are living in the golden age of life detection science. And your generation will likely see the first confirmed biosignature, the first alien ocean sample, first protocell evolution in lab, the first picture of an Earth-like planet, perhaps even the first confirmed microbe from another world. This is not hyperbole, this is a trajectory of science right now. Let me tell you a closing statement. When we first When the first alien life discovered, whether it's a microbe on Mars, a chemical signature in an exoplanet atmosphere, or living cell in an ice plum above Enceladus, you will remember exactly where you were when you heard the news. Because that moment will divide human history into two eras: before we knew we were not alone, and after. So, thank you for taking this course and welcome to the generation that will change the universe. Goodbye.